Hello and welcome to another webinar with the AEEGTA. I'm just going to share my screen. And make sure that the audio is playing. 2 seconds.
Empowering the people who work.
Let me know if you can hear that or not. Sorry, this usually works a lot better than this.
For our world. Since 1977, the Association of Energy Engineers has been leading the global energy community towards a clean and sustainable future. Founded by Alex Newman, AEE emerged during a critical time when the world grappled with the oil crisis. Today, we're a global network of over 17,000 members and 32,000 certified professionals in over 125 countries. Dedicated to implementing projects that improve energy efficiency, address climate change, and drive economic growth. AEE is a nonprofit organization dedicated to serving our members and other industry professionals and providing them with a framework so they can network, grow, and helping them stay abreast of the latest industry trends and empowering them to maintain a competitive edge through training and professional certifications. AEE developed the energy management profession. Our certified energy manager certification is available in 10 languages and now has over 18,000 CEMs throughout the world. We also have certifications in energy auditing, building commissioning, sustainable development, renewable energy, carbon reduction, and a wide range of other specialized fields.
As we drive growth, innovation, and excellence across the industry, it's crucial that we empower all talented professionals to contribute. That's where CWEL, the Council on Women in Energy and Environmental Leadership, comes into play. As a division of AEE, we are focused on supporting mentorship, networking, and scholarships for women. The technical sessions were amazing.
The conference and expo is a great reflection of where we are in the industry. A lot of the seminars, the content here is very current and very relevant. So it's a great way to come and get current in the industry. What sets AEE apart is our commitment to driving change. We are a global family focused on putting people first, making the world better for current and future generations. The clean energy transition is happening now. So join us and be part of the community dedicated to this clean energy future. Whether you're looking to advance your career, expand your network, or contribute to global climate goals, the Association of Energy Engineers is with you every step of the way. Together, we can shape the future of energy. Join us today.
So, thanks again for joining us. Please stick around for the full hour to get a 1 hour of your continual professional development and a certificate as well. So, the Association of Energy Engineers is a hub for energy professionals worldwide. It's a global organization dedicated to being at the forefront of energy innovation. The AEEGTA chapter supports energy professionals by promoting best practices in energy management, supporting professional certifications like CMVP, CEA, all the things that you saw in the video before this, creating a strong network of energy and sustainability professionals through events such as this and in-person ones, and advancing decarbonization, energy efficiency, and ESG goals in Ontario and Canada. Upcoming events that we have, we've got another webinar in 2 weeks at the exact same time as this one, and registrations for this are live. So you can hear from experts on heat recovery and energy management in data centers. We also have our signature event, which has just been posted about, and please save the date for this. Registrations are live. This is at the Toronto Marriott City Centre on October 14th, which is a Wednesday. So it's a full day of industry insights, meaningful conversations, and network. please come along. Highly would recommend. It's one of our best events. A quick word on our sponsors. So the chapter sponsors for this year, we have platinum sponsors in Inspire, Carbon Cap, Edgecom, Enbridge, Armstrong, who you're hearing from later today, Ambient. Gold sponsors are Honeywell Forge and Grundfos, and silver sponsors are Ladico, Kilmer, ENS, and Mitsubishi Electric. So, without further ado, I'll introduce our speakers. So we have two today. One is Anila Chakma, and the second is Fernando Vasquez. So this is on optimizing domestic water, booster systems, reducing energy use, improving performance, and unlocking incentives. So I'll start with introducing Fernando. Fernando is a sales manager for Armstrong Fluid in the parts and services part of the business, focused on energy retrofits and connectivity services. So data analytics about energy. He coordinates all of the Armstrong service centers in Ontario, and he's been with Armstrong for 11 years and has a manufacturing and, well, came from paper and chemical manufacturing and is a mechanical engineer by trade. Anila is a, sorry, 2 seconds, I have it's written down. She is a energy management engineer at Armstrong Fluid Technology. She supports the sales team with energy calculations and technical analysis for HVAC and hydronic retrofit projects across Canada. She has a focus on retrofit and energy optimization projects, and you'll hear more about that later. She worked closely with utility companies, contractors, efficiency consultants, and end users to support energy efficiency incentive applications and implement solutions that reduce operating costs and improve building performance. So with that, I'll hand it over to our two speakers today. Thank you very much.
Thank you so much, Aidan, and thank you everyone for joining. We can see we have around 65 people joining in this room, and I welcome you. Without further ado, I will begin what I have prepared for you. So today we're again, thank you so much, Aidan and AEEGTA for the opportunity and all the support in putting this webinar together. As Aidan mentioned, it will be me. I'm Anila Chakma. I'm the energy management engineer at Armstrong Fluid Technology. I've been with the company for 2 years now, and I've been working closely with Fernando, who also supports the retrofit projects, supporting all end users, customers, everything. So let's go ahead. So on today's agenda, I'll start with a brief introduction of Armstrong, then discuss the constant and variable speed booster systems, followed by the importance of right-sizing the booster. I'll share the details of Armstrong booster solutions, and we will discuss the incentive supports that we provide, and then we will finish the session with a Q&A. I request if you have any questions during the webinar, please keep them for the Q&A session, so we are good with the time for the webinar, and that gives us the push to go ahead. Just a quick introduction to Armstrong Fluid Technology. We are a global organization.
We can't see your screen in case you're sharing that.
Thank you so much for stating that. All righty. Let me know if you can see it right now.
It's just loading. That's it.
Perfect. Okay, I had this is how it was looking and all the agendas, and we are coming to our global presence. So Armstrong is a global organization with manufacturing plants and offices across North America, Europe, Asia, and other regions. Our headquarters are in Toronto, and our focus is on developing intelligent, energy-efficient solutions for building mechanical systems. And Armstrong began its journey in Canada, and it's been proudly Canadian since 1934. All right. Before we get into the energy efficiency, let's quickly look at what a booster system actually does. Buildings decorate the landscape of major cities around the world. Every building requires clean, safe water for basic human activities such as drinking, cooking, washing dishes, or showering. The role of the booster pump system is to increase the pressure of the domestic water supply by the utility if it's not adequate to supply the upper levels of the building. In North America, municipalities typically offer 30 to 50 psi of pressure at the interface of the building and the city supply line. And each municipality guarantees a different supply pressure. In Toronto, it can typically goes around 40 to 60 psi, but I have seen 80 psi as well if you go closer to the lake. But the minimum supply pressure that guaranteed by the city is actually only 30 psi. So by the time we have this water pass through the RTZ backflow preventers, the building piping and valves, and it already loses like 5 to 10 psi pressure at this range. The city pressure supply only adequate to supply the boost pressure up until first few floors. A booster package purpose is to provide the additional required boost water from the city supply line to critical fixtures. So critical fixtures would be at the topmost floor of the building, and in buildings with penthouse mechanical rooms, the critical fixtures may have different pieces of equipment that require highest supply pressure. So in often small buildings that have little boost requirements, elect to use standalone pump in place of a booster package. But the concern with that is it does not come with the advanced controls or the redundancy. Before we move on more, we also want to discuss the drawdown tanks that we have. Armstrong also provide the booster with the booster, the drawdown tanks also come, and the purpose of the drawdown tank is to hold additional pressurized water to maintain pressure in piping system and supply small demands to allow pumps to be shut down. This way, if a toilet is flushed at 2 a.m. in the morning, the booster package does not have to come on immediately to satisfy the system requirements. Some manufacturers require the drawdown tank to assist their PNID in determining no flow conditions. When the system has no demand, the water being pumped by the booster has nowhere to go but the tank. So once the tank fills up, it signals the booster that the system demand has been satisfied. Armstrong actually does not require a tank to assist in shutdown sequence because with variable speed booster system, a traditional large drawdown tank is generally not required as the pumps can modulate their speed to match the demand. However, depending on the application, a smaller pressure tank may still be recommended for pressure stability and very low flow conditions. We are back to talking about booster pumps. So booster pumps are like any other HVAC pumps with the main distinction being the specialized controls to control the flow according to the demand load suited for an open system. So the water leaving the booster does not loop back to the booster. This includes the control logic on staging the pumps and other advanced operational features. Booster packages, as the name suggests, are packaged units that are delivered prefabricated and pre-tested to site conditions. Walking into an old mechanical room, you may see booster packages that looks like this, and that's standalone pumps connected to a single controller. And from there, we have the variable speed booster, which now has the control panel connected and the pumps supplying to meet the demand. We will discuss more as we discuss a solution at Armstrong, but let's focus on how the pumps are looking right now. So the good news is all new buildings are going with variable speed booster. because it's energy efficient and the control is just great for the operations. Now, if we focus on retrofit and energy upgrades, if you have a building and want to reduce the energy uses, the one easy step you can do is to replace the older system with the most efficient one, and also ensure the upgraded booster is right sized. Here we have two photos of constant speed older booster system, and this boosters using the pressure reducing valves. This is the pancakey looking things. In this photo, it's blue, and then we have a little even older ones that maybe did not get the paint job recently. These are the PRVs that is helping. So the PRV dissipates the excess pressure to maintain a constant downstream pressure, which results in unnecessary energy losses. And the booster pump operates at full capacity, regardless of actual water demand. I'm talking about the constant speed one. So they often generate more pressure than the building requires. So what is the problem with all these constant speed boosters? The losses from the PRVs increase the utility cost and can also contribute to higher water consumption through increased flow and leakage associated with the elevated operating pressures. Though the traditional PRVs work well, they can cause a lot of problems and additional maintenance cost. And these PRVs are the reasons that the pressure drops across the PRVs can be from 10 to 20 psi. Also, nearly 90% of the time, the building water demands is only about 30% of the booster system design capacity. We need a system that acts with the demand of the building and not running 100% all the times. Again, just to summarize, what are the consequences of operating the booster system this way? We have higher energy consumption because the pumps are producing pressure that we then reduce through the PRVs. Higher pressure can also lead to more leakage and wasted water, as well as higher water consumption at fixtures. And finally, running the equipment harder than necessary can contribute to additional wear and higher maintenance cost over time. Now, let's talk about the solutions. Before we go more detailed into the VFDs, it is very important for us to understand what we planned accomplishing in applying VFDs, because that is the solution. Our primary objectives would usually be, we would like to reduce the energy cost, we would like to reduce the system shocks, we would like to be able to monitor the system performance and allow the user to easily adjust a system to real world situation. The proposed variable speed booster system eliminates the need of the PRV. That's the first, by continuously adjusting the pump speed to match the building's real-time water demand. And by producing only the pressure required, the system delivers consistent water pressure while reducing the energy consumption, minimizing mechanical wear, lowering the maintenance requirement, and improving overall system efficiency. Here is a real example of the impact of right sizing and upgrading to variable speed system from a constant speed booster. So we had existing constant speed booster with 3 pumps, that is 5 horsepower and 2 7.5 horsepower. And after looking at the building actual demand and the water consumption data, we have came up with a solution that is a duplex with 5 horsepower pumps. So we reduce that. And then I also put the calculation that we provide from Armstrong that shows 75% energy savings, and that is roughly 50,000 kilowatt hours saved annually. And with that math, the simple payback is 36 months after accounting different incentives that we may have available from the utility and avoiding the repair cost. This is a good example Why, when replacing existing booster, we shouldn't just automatically replace it with the same capacity. We should understand what is the building actually needs. We have another example here, and this one was a triplex with three 30 horsepower pumps, and it was for a hotel. So the comfort of the guest is more prioritized. And so when we sized it, we went with a 25 horsepower triplex set. Again, it's still lower the horsepower, and the best part is they received incentive around $60,000 from Save on Energy. We will come back to the detail of the incentive by the end of the webinar here. I just wanted to give you guys a look of what we are doing in Armstrong and what we're gonna more discuss deeply into this webinar. All right, so now let's get back to the sizing the booster. So for boosters, you need two things: pressure and flow. So the pressure is relatively straightforward compared to the flow. We need enough pressure to serve the highest and most critical fixtures in the building. Flow is where it becomes more challenging. There isn't one universally accepted method for determining peak flow, and historically we have tended to be conservative because the risk of undersizing is obvious. You don't want to undersize. Oversizing, as long as it works, everyone's happy. But the oversizing has consequences too. As you can see from this typical 7-day flow profile, the building spends most of its time at a very small percentage of the peak flow. So selecting a booster around what happens only at peak condition can also mean operating an oversized system for most of its life. That's why understanding the building's actual demand profile becomes so important when we select a booster. Let's start easy with the head, the pressure sizing. The booster needs to provide enough pressure to overcome the elevation of the building, which is the static head, along with the friction and other system losses, while still maintaining the required residual pressure at the top of the building. We also take account the available incoming CD pressure, because the booster only needs to provide the difference between what is available at the inlet and what is required at the top of the building. So the method of adding all the required pressure becomes adding the residual pressure with the friction head, the static head, and the package losses, and subtracting the series supply pressure. So pressure is relatively straightforward to calculate. Flow, and this is a real life example of a 25-story building that is in Toronto, and again, the number of floor in this building was 25, starting from the where the booster was located to the mechanical top floor of the building. And assuming each floor is approximately 10 feet per floor, the static head becomes 250 feet, adding approximately 10% for system losses. That brings the total to around 275 feet, which is about 119 psi. And we add the 40 psi of residual pressure to make sure adequate pressure is maintained at the top of the building. From the total, we subtract the available CD pressure, since the municipal supply is already providing the part of the required pressure. The remaining pressure is what the booster system needs to provide. In this scenario, that is 109.047 psi. And starting for the flow calculation easily, so we assume a unit in a condo building requires between 0.5 GPM to 0.66 GPM per unit. And it's an easy calculation for 317 units, and calculating that is 209.22 GPM. But we will discuss how this number comes up and how we actually do the calculation of flow in the field. So the three most used methods are as listed. First is the keeping the existing sizing. The motto is like, if it broke, don't fix it. That's how a lot of the older buildings have been performing, and we are losing energy through it. This is only feasible for the retrofits, does not apply to new construction, does not account for upgrades that might have been added to the building or existing boosters since installation, which can be adding high efficiency fixtures so you don't need as much flow, changing supply pressure renovation, or existing booster may be oversized, the system leakage that has going with this booster since it has been started. The second we have is the measurement and verification. This is the most accurate means of determining flow, but only under the right circumstances. This is also only feasible for retrofits, does not apply to new construction. These are this process is very dependent on project specific, such as you have to measure. There are some measurement that may not be available. We look at the water consumption bill, but the flow rates not represent full demand building. When fully occupied, let's say you put a flow meter in, but at that time the building was not fully occupied. So when it's occupied, and variable of occupancy happening through in the building, and especially for highly variable occupancy building types, which are hospital, hotels, and arenas, you have different amount of occupancy at different times. Also, the seasonal demand variation for summer and winter, time commitment also required to do accurate representation of this method. The another one is the fixture count, and this is the most common method that is being used. So it assigns a weight to each fixture type and converts total fixture counts to flow rate. The issue that it is a bit outdated, and also you are not running all the fixture counts at all times. So all of these methods eventually oversize the flow that a building is required. And we are gonna more talk about the challenges that comes with the first two methods, that is the keeping the existing sizing and the measurement verification. Changes of fixtures, like you are going from a 50-gallon flash toilet to low flash where you need less amount of water. Changes in the building design, building can expand, the units of the building maybe got distributed differently, it can go down or it can go high up. Also, the daily flow changes from time to time, changes in standards and codes, that also happens from time to time. And then all the pumps, they have, with time, they will build up different, oh, my apologies. Change the theoretical calculations could not be extensively tested on very high fixtures count scenarios like high rise building. As I was saying, over time, corrosion scales and debris can build up inside the piping, restricting water flow and increasing pressure losses. This can affect the flow and the pressure that the booster system needs to provide. Now, this graph shows 4 different sizing standards, mostly based on Hunter curves. If you are an mechanical engineer, I believe you are familiar with that. It has been developed in 1920s. And here are different sizing standards that IPC, the International Plumbing Code, the UPC, the Unified Plumbing Code, and that is applied to the same building. And you can see that each standard gives us a different required flow, despite being based on same methodology. Technically, different standards give different estimates, all of which are oversized. So for example, the exact same building, one standard is giving us 480 GPM while the another is giving 330 GPM. That's about a 45% difference. Now, in this graph, we have included what we get from Armstrong upgraded tool. And you can see that the Armstrong upgrade tool results in a lower required design flow, up to 50% lower in some cases, depending on who you are comparing it to. And this allows us to right size the booster system and potentially reduce the initial equipment and installation cost. Here, we are looking at the capital cost. So if you were following the flow and head of the standard flow and head that's available and comparing it with the what we came up in Armstrong, you can see that there's a 34% reduction in capital cost and a 49% increase in annual energy savings. So by selecting a booster that better matches the building actual demand, we reduce the life cycle operating cost. And so overall, right sizing gives us a smaller design flow, lower upfront cost, and greater energy savings over the life of this system. So how did we achieve this energy savings? Simply focusing on the pump affinity laws. Flow changes directly with the speed. So if we reduce the pump speed by 50%, the flow also reduced by 50%. Pressure changes with the square of speed. So the same 50% reduction in speed gives us about 75% reduction in pressure. And the biggest impact is on the energy because energy changes with the cube of the speed. So theoretically, reducing the speed by 50% can reduce the power requirement by about 87%. This is why variable speed operation is so important. And when the building doesn't need full flow and pressure, we can slow the pumps down instead of running them at full speed, which can significantly reduces the energy uses. The fact is that HVAC and plumbing is dominated by part loads. In the past, we would size equipment to full loads as we did not have the proper technology. But with technology advancement, with redundancy and everything, we don't need oversized equipment anymore. Oversized equipments with poor efficiencies because most of the time those equipment would be running at full load at a very small fraction of time. The industry has been implementing solutions that take advantage of the part load phenomena, and the energy savings comes with it. Once the flow and the head of the booster package is determined, the values can be easily entered in our Armstrong Adapt to give you the various booster options. So you put what is the total flow that the system needs to work with, the suction pressure that you are receiving, and the boost pressure that it requires. You can go with the standby, but more we focus on the more we run our pumps more efficiently, we don't need the standby, the redundancy of it as much anymore. A shift towards the lead and lag operation is taking place. Modern booster still use the N+1 redundancy where they allow active duty pumps would be at the same specification and then an additional pump included for redundancy. But the best situation is if you are not keeping one pump just sitting there. If you were running two pumps at 30% instead of running one pump at 60% of its capacity, that gives us more energy savings and uses, of course, less energy. Now, when we look at the pump curve of a booster system in this scenario, we are going with a triplex booster system. As you can see that it has it has a bit room for additional head. Also, our ADAPT system already incorporates 5 psi when it's finding the booster. So we do that. So if the CD pressure decreases with time, the booster is still working to meet the demand. Also, the operating point is slightly to the right of the best efficiency point that maximizes the efficiency at part load conditions. The least number of pumps and the smaller horsepower motors would adequate to lower cost. Now, as we have discussed what we found using the Armstrong booster sizing tool, this is to introduce you to the Armstrong booster sizing tool. This tool can be used for both new booster sizing and retrofit applications, but it's more efficient, has more tool to calculate and compare with the existing booster than a new booster system. The process starts with gathering information with the site survey form, along with the building water consumption data. Using this information, we determine the building's actual flow and pressure requirements. Once all the information is analyzed, the tool provides the right sized flow and head requirement, which then we use to select the appropriate booster system. So when we are evaluating the existing booster pressure for the booster sizing tool, these are some key pieces of information we want to collect. The suction pressure coming into the booster, the discharge pressure, and the existing flow capacity. For discharge pressure specifically, we can look at the nameplate of the design pressure, take actual readings from the pressure gauges, and if there's a PRV, record the pressure both before and after PRVs. A lot of the times, a lot of the existing system may not have that, but if it does, it actually shows how much pressure you're losing at that point. The difference of the pressure coming in and the system pressure required is actually shows you how much pressure you will be needing. Now, moving on for the flow. Again, we are trying to count the fixtures. So we need the number of units so we can understand how many bathrooms each of these units have. Other fixtures such as washing machines, dishwasher, laundry tubs or kitchen sink that's available in the building, and then from different units to public fixtures that can also have different dishwashers or hose beam or laundry tub for the whole building to use. So putting all that into calculation, and the most latest addition to our booster sizing tool is the ability to analyze the building's actual historical water consumption. Ideally, we collect 1 to 3 years of water bills with at least 12 months to the least. The sizing tool uses this information to estimate the building's peak water demand rather than relying on theoretically fixture calculation. This gives us another data point to help avoid both over and undersizing and select the booster that better reflects how the building actually operates. Once we enter the building information, the fixture counts, existing booster data, and historical water consumption, the sizing tool compares the existing methods and calculates the expected flow and pressure requirement, and then we review these results with our end users, with our service partners, and then we make the final booster selection. So the overall goal is to combine the theoretical sizing with actual building data to select the booster that better reflects the building's real operating needs. Coming back to why right sizing is so important, as I have mentioned so many times, that the oversizing is so common, and the impact of an undersized booster is just so immediate. The oversizing is less obvious, and it may happen over time, but the oversizing in real long consequences includes higher energy use, increased water consumption and waste, additional maintenance, and potentially reduced occupant comfort. So bigger isn't necessarily safer or better. The goal is to select the booster that actually matches the building's need. I'll click I'll quickly touch on the EPIC calculation, that is the ROI and the energy performance improvement calculator we have in Armstrong. So it compares the existing booster pump information and it compares with the efficient variable speed one, and then it provides you the output with estimated energy savings, estimated annual cost savings, estimated reduction in GHG emissions, and simple payback periods. Going back to the example that we have used, if you take another look at this the ROI report, you can see the 75% energy savings, that is around 50,000 kilowatt hours annually, and the simple payback, including the incentive and avoided repair cost, is around 36 months. So what do we have in Armstrong booster packages? We offer configurations from duplex through quantiplex with 5 pumps in one package with both duty and duty standby operations. Our packages use design envelope permanent magnet motors with NEMA ultra premium efficiency. Depending on the configuration, our Armstrong booster can handle up to 2,252 US GPM, and boost pressure is up to 669 feet of head for duty standby. That is, the flow is around 1800. So this gives us the flexibility to serve anything from smaller residential application to much larger buildings. I think the smallest we have is 1.5 horsepower duplexes. And then the highest we have is the 60 horsepower ones, each pump. These are I have few slides that is showing the efficiency advantage of our DEPM motors at both nominal speed and part load operation, around 50% speed. DEPM motors maintain significantly higher efficiency than the conventional induction motors with VFDs. Again, this is just a comparison between Armstrong and Armstrong, but instead of the induction motor, now we are using the permanent magnet motors, which are the ECM motors, and this translates to meaningful energy savings. Here's another benefit showing the lower noises, as the graph shows across the different motor sizes. DEPM motors operate at noticeably lower sound levels compared to the industry standards. This is very valuable for residential buildings where some units are right next to the mechanical room. So the mechanical room noises can be reduced. Another benefit is the reduced weight. So it's easier to transport, handle, and install. Also, not but least, I know a lot of our end users and service partner ask about the lead time. So our DPM lead times is around 12 weeks right now. At Armstrong, we are really taking the lead time very seriously and trying to help support to get the boosters at given times at the least lead times that we can provide the booster at. Okay, now another most interesting part. You might be already familiar with incentives that available in Ontario right now. I'm focusing on Ontario's, and Armstrong actually provides end-to-end support. So we help you identify what kind of incentive that might be available. This not only goes for boosters, it also goes for our different pumps and the optimization tools that we have available. So we assist you with all the application and support you with anything that might be required from the from whoever is giving out the incentive. In this case, I want to focus on what we have in Ontario with the Save on Energy program, and for booster, that is the prescriptive incentive, replacing an existing constant speed domestic water booster with a variable speed system, and that provides us 1200 per horsepower incentive up to 100 horsepower. Both Armstrong DE and DEPM booster packages are available. As shown in the example, the 12 horsepower system would receive $14,400 in incentive. And this is an example that we have actually worked to get the incentive secured for our customer, around $60,000. This is the email we have to support the end user as applicant representative, as the application needs to be from the end user. So again, that's the email. If you ever have any questions about incentives, you can keep this and you can reach out to us. That's not the only place you can go for support. We have, again, we focus, as an energy management engineer, I focus a lot on retrofit projects, and Fernando with me, who focuses on supporting a lot of our Armstrong service partners, and also he has been with the company for so long. If you have any questions, anything that you want to bring to our attention, you can always reach out to me or Fernando. That brings me to the end of this webinar. Hope we are still good on time. So we'll be taking any questions you may have on booster selection, energy savings, incentives, or any specific projects.
Thank you very much, both of you. That was very, very interesting. I have a couple of questions in the chat, and please, any of our attendees, please feel free to add some just there. Andrea Dwight says, what is the payback without incentives? Now, I think, yeah, on you go.
Okay. No, thank you so much. Well, that's a great question. It will have to be answered each project, because the savings are not the bigger the size of the pumps, the bigger the savings, and the smaller the payback will be. But given from all the projects that we have reviewed, the savings is, I can tell you the savings is between 65 to 75%, and with and without the incentive, that reflects, it goes from, it can be from 3 years. We have seen as low as 2 years and as high as 6 years or even 10 years. So again, that it depends on the size of the building, size of the booster, what you have in the existing system. But what is constant is the savings that is shown between 65 to 75% when you are going from constant speed to a variable speed booster system.
Perfect. Irina Rosen has asked, can you share the Armstrong tool that we can check the sizing of booster pumps, or does Armstrong offer this assessment?
Armstrong offers this special supporting you with this tool. So what we can provide is, if you want to reach out to me, I can provide you the site survey form, which lists all the required data, and then we take that data into our system and we come up with the required flow and head that might be appropriate for the given building.
Perfect. So just for all of our attendees, I put the emails of our speakers in the chat if you want to reach out for more.
Thank you so much, Aidan.
Jelani Faisal says, for incentives, are your motors listed as approved?
About the motors, yes. So all our the variable speed booster, especially the variable speed boosters, they are listed with Save on Energy, and they recognize our the models, the boosters that we have. I believe the newest incentives that's available is the cold water pumps as well. That's actually not for the boosters because the boosters is prescriptive and it's very generous with 1200 per horsepower. Um, so I believe that's what you are asking. So, and if it's not, again, we are always in touch with Save on Energy. If they have any questions, we always can support you, meet with them, or forward us the email that the kind of questions they have before or after approving the pre and post project application with Save on Energy.
Perfect. Hopefully that answered the question. Chris Barry has said, you had an example earlier on. Can you please walk us through this 60 to 75% savings?
Happily, I will just going to open the presentation real quick and share it so I don't forget. Here we have the shared screen and here we have the presentation. Going back to, okay, I think we went a little too far. Okay, all right, here is the calculation. So the annual energy savings is 6,557. And in this scenario, we have calculated the energy cost at 0.13 cents per kilowatt hour. And the back calculation does this, multiplies that with the annual consumption reduction of 50,000 kilowatt hour, and that's what gives us this number, and that's what shows in the percentage. So this savings happens for when you are doing this, takes into the corporation the variable speed because you will be running your pumps at part load, not full load. And it also takes consideration the permanent magnet motors that we are using in our boosters. Also any kind of the repair cost. Most important, the PRVs. So you are eliminating the PRVs where you are not losing 10 to 20 PSI. So the PRVs, the part load operation, the permanent magnet motor, all of that gives us this number, the reduction, that's the 50,000. And when it comes to incentive calculation, let's say if you want to go with custom application instead of prescriptive, Save on Energy asks us the questions how we got this savings, and then we go in detail, and we have been approved a lot of our incentives with proving this reduction as well. I hope that covers what you were asking for, Barry.
So, Faisal, I think that might have answered your question. If not, let me know. Vladimir Marinich says, are your motors generally off the shelf or exclusive to one manufacturer?
Fernando, you want to answer that?
I'm sorry, you're asking me if...
Are your motors generally off the shelf or exclusive to one manufacturer?
Oh, no, yes. No, the boosters are built on order. Yeah, we don't. We're trying to work on stocking some popular models, some popular sizes, and then through software adjust them for the application. But today they are built on demand. Yes.
Thank you. And Chris Barry had a follow-up question, I think. Wouldn't the majority of the savings be realized by changing the pump runtime?
Yes, that's what we change, the runtime. So the load, our calculation looks at the load. So it's at maybe the pumps is running 100% of, so it also varies on the type of building that we are looking for. So we can have a hospital building or an apartment building. The load is not going to be same. So we have standardized this calculation based on the load. So maybe a hospital is running 70% of the time at 5 hours or 10 hours. At 30%, that's 7 hours, or at 10%, that's 12 hours of time. So that's how we establish this calculation and the savings. So yes, you can, this savings can be realized by changing the pump runtime and at what load the pump is running.
Yeah, and if I may add something, keep in mind that the booster runs under variable speed. So it adjusts the speed and the flow based on what the building is actually requiring. So not only the run times, but how the booster is reacting to the building, supplying only what is needed. And there's a feature which is called the shutdown, the no flow shutdown. So when there's no flow at all, let's say at midnight in a condominium or so, the booster automatically shuts down. Keeping the pressure, but the system automatically shuts down until there's demand and then starts again. So when you combine the runtime, the variable speed, and all these factors, that's where you materialize the savings.
Perfect. There's a few more follow-up questions, but unfortunately, we do have to end it there just to finish off on our final bit. But the emails of the speakers are in the chat, and I have seen that we will share the contact information on the last slide as well, and the slides will be sent out after the fact. So I will just share my screen. I think that should be it.
Perfect. I have answered one or two questions in the chat, but yeah, always feel free to reach out to us. Thank you again, everyone, and thank you so much, Aidan, for putting this together, and AEEGTA. Thank you.
Thank you very much. So we have just a slide here. You can scan the QR code to become a member. Just a reminder, if you've been for the entire hour, you'll get an email with the CPD certificate, the recording of the webinar, and also some slides as well. So we have a membership for $60. It will get you discounted entry to some of our events. Students, we also have for $20. So finally, just want to say a heartfelt thank you to our presenting speaker and the participants as well for making time out of your busy day to come and join. We hope you found it insightful and answered some of the questions you came with. And if you have any more, please reach out to our speakers or through us directly at president@aeegta.org or on our website. We hope to see you in our next webinar and our next in-person event. For now, thank you very much and have a good rest of your day.
Thank you. Thank you very much.